Welcome! In this video I want to show you how it's possible to set up Matlab Simulink together with a Texas Instruments Launchpad to drive your motor application. And the best thing, we do this without writing one line of C code. Here you can see the result, what I'd like to show you today. At the left side there is a Matlab Simulink with commonly used blocks you might already know, like the Addon or PID Control, scopes or displays. At the right side, this is the scope you can see here, showing us the desired speed, the actual speed, and the difference of these two figures we call the error signal. At the upper right side we will see two coupled DC motors. Today we use just one of them, as well as the power electronic circuit and the Texas Instruments Launchpad with the USB connector to the computer. The communication now is running with Simulink to the target board with around about 9 megahertz or 9 megabit per second. And without recompiling the whole system, I can change the speed. And we see the parameters changing. We have desired speed, actual speed, and the error signal, and can directly change the parameter out of Matlab Simulink. You might see that the change of the shaft speed from the USB camera is not synchronous to the scope we will see here. This is, I use a pretty poor USB camera, so there's kind of some kind of delay between the communication USB camera and this viewer. I cannot only have manual figures for this desired speed, I can also set up a step response, and of course the parameter of this step response I can change directly without recompiling the whole system. So now let's jump to 1000 RPMs, or we can jump to 2000 or 3000 RPMs. No, 3000 is too much. 2500 RPMs, and we can directly check up the parameters we set up in the PID controller. All this is done without recompiling. All we have to do is to set up the processor in a loop system from Simulink together with the Texas Instruments Launchpad. And how to do this I will show you at the next slides. Now let's have a look at the hardware components we need for our setup. First of all, we need some kind of brain, and in this case I use the Texas Instruments Launchpad F2069 to control our power electronic circuits. This board is equipped with a 30-bit microprocessor. Then of course we need some kind of customized hardware. To drive as many as different motors during my lecture, I use a customized hardware which is capable to drive DC motors, BLDC motors, induction motors, and so on. You can also buy your specialized hardware at the Texas Instruments shop, especially for this Launchpad. There are a lot of different hardware boards available which fit directly to the Launchpad. Then of course we need some kind of motor. In the example we have seen before, I use a standard DC motor with permanent magnets in it. Not shown here is I of course use an encoder to get the shaft speed of my motor. And this all together is the setup we need to get this motor run. Then of course we like to have a communication, not only for programming with Matlab Simulink, and this is done with a serial connection, the Launchpad comes with an FTDI chip which allows a connection speed up to 12 megabit, where we can lock parameters or data, for example, analog values or digital values. In this example, you have seen I locked the shaft speed, desired speed, and so on. And we can also change parameters. And this is really helpful feature, because as the motor is running, I can change PID parameters, I can change the gain of the step response, and evaluate how the motor, together with this setup, with this controller, reacts. You might ask, why is there another video showing us how a C2000 processor is programmed within Matlab Simulink? And the answer is very easy, because either there are a lot of samples which are too easy, they just blink an LED, or turn it off and turn it on, or I think they're much too complicated. And this is the reason why I decided to make another video showing us the possibilities from the Texas Instruments Launchpad together with Matlab Simulink. The next question is, why should we program a microcontroller with Matlab Simulink? And of course you do not have to. It's just an offer to make it easier. And for me, I had never fun programming microcontrollers with C code. And if there is something easier, I'd like to have it. And especially if you look at difficult control structures. The second answer will be, it is much easier to connect your target hardware with Matlab Simulink, and you can directly exchange parameters as the program is executed. In this slide, you will see the content of the next few topics we will talk about. First, we have to look at Matlab Simulink, especially what we need to run the embedded coder system. Then we need some changes at the target hardware, our Launchpad. Then we go on, and I will show you how to read GPIO ports, set up PWMs, and read ADC ports from our Launchpad directly within Matlab Simulink. And at the end, we will once more look at the application, our motor PID control loop, in detail. At the beginning, first go to the Addon Explorer within Matlab and install or search and install the embedded coder support package for Texas Instruments C2000 processors. There is some third-party software needed to be installed, especially the CCS Code Composer Studio from Texas Instruments. But this application will show you in detail what it's to do, so normally no big issue. After everything is installed correctly, please check within the device manager if you can find a serial connection to your board. It is named XDS100 class USB serial port. The last step is to check if all jumper settings are correct at our target hardware F28069. Now we can prepare Matlab Simulink to connect to our target hardware. Go to Matlab, open Simulink, start a new project, and go to the hardware settings. There you'll find a drop-down menu where you can specify your hardware board. There you'll find the F28069 Launchpad. The next step, we have to set up the connection. And this you will find during external mode, where you have to set the right COM port. And this is the COM port we have seen before during the device manager. Serial communication interface A is used to communicate with Matlab. And Here you can specify the desired baud rate up to 12 Mbit. Now I want to introduce the hardware to you, and if we have a look at the hardware, we'll see the red board, the evaluation board with this 32-bit microprocessor on it, and here at this side of the board you see the communication interface. This is the FTDI chip which sets up the USB connection to the computer. Then you might have noticed that with this hardware I can drive two motors, two BLDC motors or two induction motors, because I use a set of 2x6 MOSFETs. Today, to drive the DC motor, I only use these 4 MOSFETs as a full bridge to get both directions for the motor. Then I need some, or here I have some additional hardware. I can turn on, we will see later, 2 LEDs. Here we read the encoder signal, speed signal of the motor. Then I have motors are equipped with torque sensors we do not care about today. Power supply, and here is the output of our motor one we use for our demonstration. After you have installed the Texas Instruments support package, you will find within the library browser special blocks for your microprocessor. For example, for our 28069 processor, there are blocks available to read analog values, like this one here, or to read GPIO ports, or to set up PWM counters, communication, serial parallel interface, and so on. There are also some advanced motor application features available from Texas Instruments, like the Clark or Park transformation. Before we start with our main application and how to set up a speed regulation for our DC motor, let's have a closer look on how to program the hardware out of Matlab Simulink with the embedded coder. For this, I've made a setup to test the complete hardware, and if I zoom out, you'll see there are a lot of functions included, and all are programmed with Simulink. For example, we can now first let's start, and we push this monitor and tune button, and now the compiling starts. We can see the single steps within the diagnostic viewer, and diagnostic viewer starts the Code Composer Studio we have installed as we install the embedded coder app within Matlab. And now the Code Composer Studio from Texas Instrument is compiling our project. And this is one of the drawbacks using Simulink together with this with the Launchpad. It might last 30 seconds to 1 minute until you are ready to use the whole setup, or to use your parameter settings. Now we're already done. Click OK, and we see time is running. It's already 30 seconds running, and right now we can see that all these displays will get the values. So, for example, we have the power supply is 15 volts, is 47.5. The battery voltage is 21 volts, and so on. And now we can test every single part of our hardware. For example, unfortunately I do not have the switch buttons which I show you can connect, but there is a connector missing, so I cannot show you these buttons. But I can show you how to turn on and off the LEDs. I can directly turn on and off the LEDs. We can see here at our hardware, these are the LEDs. We can turn it off directly with this GPIO output pins. We do this with you go to the how is it called, a library browser and get this GPIO, and all you have to do is to choose which GPIO you would like to use. It's the green LED. In this example is connected to the port 27 and so on. Of course, these are parameters we cannot change during the program execution. This would be a recompile of the whole system. Then we can read ADC values, and ADC values are you can get with these ADC blocks. It is possible to use sampling mode or use a trigger signal, for example, a PWM signals, a PWM trigger, and so on. We also set the sample time, which means how many samples per second we'd like to read the ADC, and it's transmitted to Matlab Simulink. As we have a baud rate up to 12 megabit, we can sample and directly transmit it to Simulink with 1 kilohertz or 10 kilohertz. Of course, if we use a standalone application, when built and programmed without transmitting the data, we can go much faster than these 10 kilohertz. Then we have these gain blocks you might use to within Simulink. We can directly set parameters to multiply the output of the ADC values. We can use display blocks and so on. Then the same, like here we have temperatures values we read. I use an LM335, I think, to read the value. And what we can do now is we not only can set the gain we might use for a voltage divider, we can calculate the final temperature value. In this example, I have the equation for my temperature, and now what I do is I program the whole equation with Simulink in a graphical way. This example, we have convert from digital to a voltage value. Then we have a voltage divider, which we have to consider. Then we have to add this 2.98, which comes from the sensor, multiply with 100, add a constant, and so on. Then we do some averaging, and we get the final temperature value. This example, there is only one sensor connected, the other one is not connected, so it's the default value for open circuit. And if we talk about motor application, so we need some kind of PWM and full bridge regulation. And what I do is every half bridge here in this example gets its own block. And within this block, I can turn the half bridge on and off with the value. Then with the PWM value, I program this way. I can set to 0 to 100%. Then I can change the rise time and fall time of the dead time counter within this PWM block. Now let's have a look inside this PWM block. First, I calculate the period out if as I use the percentage from 0 to 100%. Now I calculate the period with this constant value, have a maximum count for one period is 4,500 and recalculate it to the absolute value. Then make some data conversion to an integer 32-bit value, and then we go into this EPVM block, which comes from the Texas Instruments library. This is a real powerful function where we can set many parameters. We have which kind of PVM module we like to use. Then we have the timer period. Then we can do some synchronization to other events, like the ADC and so on. Then we have two PVM compare matches. So we have the compare match A and compare match B. We can specify what has to happen if the counter is 0, if the counter is in period, and so on. Same as here. Here the counter compare values. Then I can specify a deadband unit. This is our parameters, what you have seen before, the dash buttons. And deadband period source, here's the input port. We use deadbands for both PVM 1A and 1B. And so on. And there's a lot of parameters we can apply. For this case, it's enough to set up the period, to set the compare match value, and here rise time, dead time for rising edge, dead time for the falling edge. As we have a clock cycle of 90 megahertz for our processor, we have to recalculate it, the dead time, to get the values here. I think it's in microseconds. Then we have, like I said, for this example, we have 6 half bridges applied within the circuit. So, of course, I need 6 of these half bridge control EPVM blocks. The rest of them, I read ADC values for current of the motor 1, current motor 2, and so on. Also, we use force sensor to calculate the torque of these two coupled motors, and then we have to calculate the torque and so on. Also calculate then the power of the engine, the shaft power, the electric power, input power, voltage multiplied with the current, and so on. Then we have an Hall encoder, Hall or encoder included. The hardware is in that way, built in that way. I can use either a Hall sensor for brushless motors or an encoder like I use it here for my DC motors. We cannot use them both in the same time, or unless we use two digital ports. In this case, I do not. So if I use the Hall signals, I use GPIO 19, which includes an interrupt signal, or can have an interrupt signal, or use the encoder with this ECAP module. An ECAP module is an additional function from Texas Instruments, which counts the difference between two encoder signals, and we'll get this value out of this port here, this TS port. So and then we get we can recalculate this in rounds per second or round per minute, and get the frequency, the shaft frequency of our motor. We can, of course, use interrupt functions if we have some we need some special functions and so on. So there are a lot of different functions available in the special Texas Instruments library. Now we have seen how to set up and program it, and it is really easy to set this up. We have poor graphical programming. The main difficult, or what's most difficult, is how to set the to get in detail in touch with this EPVM function, because there are a lot of or so many parameters which can be changed. The next step, the next slide, we'll see how to set up a motor application and how to set up a PID controller for the shaft speed and motor speed. Sorry, I forgot to show you the half bridges in action. So, like I said, we have 6 half bridges, as I'd like to use the hardware to drive a BLDC motor. Today we use just 2 half bridges. Together will be then 4 half bridges, excuse me. Together will be 2 full bridges. 1 full bridge for every motor. So we have here the upper 4 MOSFETs, or right MOSFETs for motor 1, the left upper MOSFETs for the motor 2. As I use the MOSFET driver, which turned off will be the lower. If turned off, the lower MOSFETs will always be turned on. So this means if I switch the high side MOSFET, the motor starts turning. Again, you see a little delay from at the USB camera from the moment I turn it on. Maybe you hear the motor running, which is in synchronous, like I turned on, turn it off. So I can change the direction of the motor if I turn now the other high side MOSFET on, or use the PWM cycle for this upper MOSFET. This is our motor 1. The same I can of course do for motor 2. And again, other direction. See here, every half bridge is can be independently changed. For every half bridge, we can independently change the PWM cycle. So that was the functionality for our half bridges. Now we go really to our PID control for one of these 2 motors. Now I'd like to show you the whole setup in detail. At the right side here, you can see the motor application itself. We can change between clockwise, counterclockwise, or to deactivate the whole motor. The output of this block showing us the motor power, input power, the motor voltage, and the motor current. Within this block, we have here the full bridge control. Each side of the bridge is controlled by these PWM, EPVM modules provided from Texas Instruments. Here we get the current measurement, we get the voltage measurement, we make some calculations, we do some average, or to get some average values, and so on. Next thing I'd like to show you is I get here some general values out of the engine. So this is temperature, it's not sensor is not connected. Then the power supply voltage. This is the round per minute, shaft speed, and the torque. We measure with 2 torques and force sensors at the shaft. Then at the beginning of this presentation, you have already seen the PID controller, which is the most powerful part within Simulink. I'll show you here today. And the good thing is you can use nearly all Simulink blocks like PID controller or switch case, conversion, data conversion, constant values. Here we build the absolute values and so on, like you are used to with all your other problems you have calculated with Matlab Simulink. There is one drawback, the dashboard buttons, there are only these knobs or switches are working. Unfortunately, we cannot use dashboard scopes if we connect to the hardware. And that's all. That easy it is. So get the engine run. Here's again my square function. But we can, of course, look in, start square function. Excuse me. We do this a bit slower. It's not that noisy. But we can also get the shaft speed, which is here. Then we can go and have a look at some other values. For example, this is the current value of the engine, which is close to 0. Then we can see here the values, voltage value, the encoder signals, shaft speed, encoder signal is coming with this ECAP module, which measures the time between two encoder signals. So the output is the time, and then we get here the frequency, and the frequencies then get out of this block with the period of 2 impulses. Then another example here at the upper left side, we see this is the temperature measurement and the input voltage measurement, and we can directly use here constant values to get the IDC resolution and the voltage divider values. So that's all of the live demo to set up Matlab Simulink together with the Texas Instruments Launchpad. I hope you can use some parts of this documentation for your own projects. See you next time.